All right, so I'm going to begin in just a minute. Let's get everything on the stream situated. Get rid of all this. Okay. Today's presentation is just, excuse me, is going to be about the first exercise from yesterday's lesson. So again, we're talking about group actions. And we were doing some group action exercises from this book, Basic Algebra, Jacobson, second edition, if it matters. This problem was on page 78, so I just wanted to clarify what was going on with this problem. I did say something incorrect last time, and I wanted to say why I was confused and show you the correct argument for proving the problem. So let's just restate what the problem was. Again, this is page 78, I believe. And I'm going to entitle this lecture Lesson 5.5, and this will be the definitive last video I do on group theory. If anybody needs any more help with group theory, of course, you can always ask me any questions or contact the email, mathpondofficial@gmail.com. Yeah. Okay, so this is just going to be, more exercises, or I'll just say correction. Right, and we're talking about group actions. This is page 78, number 5, exercise 5. Just get a quick water. Right. So last time, essentially what was incorrect was I had the wrong group action. In fact, what I defined was basically a bunch of nonsense. And I sort of realized that as I was presenting it yesterday. So maybe I shouldn't have gone so quickly in my notes and jotted that down, but let's define the correct group action today, and we'll see how we get the correct result. So let's just restate the problem. I'm going to kind of summarize it, but basically we had P is a prime number. It divides the order of the group. And it's, in particular, it's the smallest prime divisor of this size of the group. Smallest prime of the order of the group. Right? And then the problem asks us that if we have a subgroup that has index P, then we want to show that that subgroup is normal. Or an equivalent definition is that the conjugations of things within the subgroup, so if I take a subgroup H and I conjugate something in the subgroup by G, so G, H, G inverse, that thing is always staying within H. So G, H, G inverse is always an element of H for all elements of the group G and elements of the subgroup H. That's the definition of normal. Right, so here what we're given is if we're given a subgroup of index P, we want to show that it's normal. So the problem is if H is a subgroup of G and the index of H in G is P, then we want to show that this subgroup H is normal. And again, this index, I might have kind of skipped over this really quickly, but this is an important notion in group theory. This is just the number of left cosets of H in G. So this is saying there's P left cosets of H in G. And with this statement, if H is a subgroup and it has this index, then we want to show that necessarily that the subgroup is normal, that it has that normal property. So then H is actually normal. And one of the symbols in the book that's common in math terminology is if you have a regular subgroup it's less than or equals to sign. If it's a normal subgroup, so you use this, you fill in the triangle basically. It's a less than or equals to sign with this caret filled in. So H is a normal subgroup of G. Okay, that's the problem. Last time what we did incorrectly was I said that the group action was G acting on the left cosets of H in G by conjugation. But actually this action is just a bunch of nonsense. I don't even think it even defines an action. So I'm going to show you the correct reasoning. I had a lot of the notions of the idea correct. In fact, we were talked about the stabilizer in a correct way, and the way we deduced that all of the stabilizers had to be the full subgroup was correct. Unfortunately, the group action that we defined was not a group action, so the proof didn't really make sense. But right, so we have this subgroup H. The thing I think that I was confusing with is if you have a subgroup H, there's something called the conjugates of H, where you can conjugate a subgroup by an element of the group G, and then you get a different subgroup, and you can look at all the conjugates of H, and so conjugation acts on those trivially. Well, not trivially, but it acts on those just by definition. But yeah, that I was just confusing things because left cosets conjugation, I don't think that action even defines a group action at all. So the key to this problem really was trying to figure out what is the group that's acting. Here it's kind of obvious that the set that it should be acting on is the set of left cosets of H and G. Although I guess theoretically maybe you could come up with some other action, but yeah. So let's try to figure out the correct action here. Last time we said it was G acting on the set of left cosets of H and G, but with the conjugation action, that didn't make any sense. So here we're going to define the correct action. In fact, as I was presenting it yesterday, I actually, while I was writing it on the board, I realized it didn't make any sense. So, hindsight is 20/20 though. Now we can go back and get the correct reasoning. So here the correct action though is actually H. The subgroup H itself is acting on these left cosets. But the action is not conjugation, it's just left multiplication. So that's a common theme with these group actions. Sometimes we'll be just acting by left multiplication. So here, any H is basically going to act on one of these cosets. Or actually, let me rewrite this a different way. Right, so what is the action of H on a left coset? We could sort of write it like this. So if I have GH, some left coset, how does H act? Well, it just sends it to the coset, which is HGH. Just multiplies the elements, and you're looking at the left coset, which is the product of those elements. Right? So you have a coset. It acts, things in H act by multiplication on the left of those cosets. You get a new coset, right? So you're permuting these cosets around. Every element of H acts as some permutation of these cosets. Right, and then so this being the action, we had an action before written down. This is a new action, but no matter what action you have, there's always a I always want to call it the class equation or class formula, but I know that's not the name for it. But it's this counting theorem where we're counting the number of elements in a set that has a group acting on it, and there's a relationship between the sizes of the orbits and the left cosets of the stabilizers of those orbits, right? And that's basically the substance of the orbit stabilizer theorem, right? So that's just saying that the number of elements in the set that's being acted on, in this case it's the number of left cosets of H and G, which by assumption, we assumed that this had size P, the smallest prime dividing the order of the group. But the counting theorem, if we count the sizes of the orbits, right, the sizes of the orbits are, we just sum over one representative from each orbit, and it's the index of the stabilizer of that element under the group action. And the stabilizer is always a subgroup of G, so in particular, this index here always divides G, right? So either this index is 1 and the stabilizer is the whole thing, or this number is some divisor of the order of the group. In particular, it has to be bigger than or equal to the smallest prime divisor, right? Because if it's a divisor, then it's definitely greater than or equal to the smallest prime, unless it's 1. So that's the big stipulation here, is that these numbers could all be 1, right? And in this particular case, we're going to actually show that they have to be all 1. Because this is the smallest prime dividing the order of the group, there's no way we can add all of these numbers up if they're all greater than or equal to p, unless there's all just one subgroup, right? But there's but there's at least one orbit that we know has size 1, which is the identity left coset, right? Because every element in H sends the identity left coset to itself, right? Because if you multiply by something on the left in H, you're still in H, and so you don't change the coset, right? So I'll write this down in a second, but there's at least one of these that is 1, and therefore, since p is the smallest prime number, you can show that they basically all have to be 1. Because if they weren't 1, then we would have at least 1 plus something that's greater than or equal to p, and then that can't be equal to p. All right, so a little hand wavy, but I'll try to write that all down after. But again, just to summarize, we have this group action. H acts on the left cosets. It acts by left multiplication. We get this counting theorem where the number of elements in the set being acted on can be represented as a disjoint union of the orbits, which each have size, which is the index of the stabilizer of the representative of the orbit. And then we said all of these numbers, there's at least one of these numbers that is just 1, and since they're adding up to p, all of the other numbers have to be also 1, or else they'll add up to something bigger than p. And so really it's very dependent on p being the smallest prime divisor. If that wasn't true, then this argument wouldn't work. Okay, so basically, yeah. So that's that. I'll just restate what I said at the end there for the next part of the argument. Right, so H acting on the identity coset of H, which is the identity times H. This is equal to H big H, which is just, since H is in H, multiplying, something within H. H is a subgroup, so it's closed, so this is just H basically. And this is true for all H. So no matter how we act on the left by something in H, it doesn't do anything to this left coset, and that tells us that the stabilizer subgroup of H is all of H. So no matter what we plug in here, it acts as the identity. So that says that when we wrote down these stabilizers, the index of these stabilizers, and we wanted to sum over the representatives, right? Well, one of the orbits is the identity, right? Because no matter what I multiply it with on the left, I get back the identity. So the stabilizer for that one is the entire, should be actually H, because here our group acting is H. So for the identity coset, it's an orbit of size 1, and the stabilizer is the entire subgroup H. And these numbers have to add up to p, so we have 1 plus something equals p. And potentially we have, a sum with many other elements here, but if any of these stabilizers are not the full group, then we would be adding numbers here that are at least size p. So we'd get 1 plus something that's at least as big as p plus something that's at least as big as p. And there's no way that can equal p unless all of these numbers are just 1, right? So basically I'm arguing that all of the orbits have size 1, that all of the stabilizers are just equal to h. So no matter what the left coset is, not just the identity coset acts, or sorry, not just h acts as the identity on the identity left coset, but this is actually, I'm claiming here, a stronger statement that h acts as the identity under this action for any left coset, not just the identity, but if you pick any other coset as well. And that's just a restatement of the stabilizers being equal to h here. So a little bit hand wavy, but hopefully that makes sense. Essentially, I'm just arguing that all of these stabilizers have to be equal to h. And so I'll write that here. So all of this implies that the stabilizers for each orbit is equal to h, no matter which representative we pick, no matter which orbit we pick, it's always h. Basically everything acts trivially in h. Okay, and then we're going to use this to get the result that we want. So, and the intuition here is that we're acting on the left by h. We want to pick something, the inverse of something here as the representative, and then when we act by h, it's going to not change anything. So we'll just get the same thing back. And then we'll do a little quick algebra to show that actually what we showed is that h is normal. Questions? Okay, so basically, I'll just rewrite what we had at the end there. Basically, we showed that the stabilizers for the action are equal to h, and this is true for any xi, which was in the set being acted on, which was the left cosets of h in G. Right, so in particular, if I pick the left coset, which is G inverse, so I just pick an arbitrary element G from the group, and I pick G inverse H, and this is an arbitrary left coset. I know that its stabilizer has to be equal to H, so when I multiply on the left by H of this element, it shouldn't change the left coset that I'm in. So basically, H times this left coset should just be the same thing, the original element. It should act trivially, so I should just get G inverse H. But what does this mean? If I multiply on the left by G, and I cancel this G inverse, that really just means that G inverse H is equal to the identity times H, which is just H. And if G inverse H is equal to H, well, that means that G inverse is in H. That's the only way that I can multiply on the left and stay within H, right? If I multiply by something outside of H, I'm going to end up outside of H. So this is actually one of the properties. I think I probably didn't specify this super precisely in the small time I had in the lessons, but if you want to show that two left cosets are the same, they're the same if and only if the elements that are represented in them, if you take the first element times the inverse of the second element on the right, it should be within H. So in particular here, the inverse of the identity is just the identity. So really, it boils down to saying G inverse is in H. So that's, if this is true, then that just means that G inverse is in H. And because this was true for any xi, any representative, it doesn't matter which left coset I pick. It doesn't matter which G I pick. This is true for any G. And also because the stabilizer is all of H, likewise I can pick any H here, and this is also true for any H in big H. And this is the definition of normal, people. So if you have a subgroup and you pick elements from the subgroup and you conjugate by elements from the entire group and you stay within that group, that's the definition of normal. So if GH, G inverse is in H, for all G in the group and for all H in the subgroup, then that means by definition, so for all G in the group and for all H in the subgroup H, well, by definition, this means that H is normal. So if you conjugate any element in H, you stay within H. That's the definition of normal. We showed that that's true, and so that finishes the proof. So again, just to summarize what we showed here, if you're confused, we had an arbitrary abstract group. We had a prime number P, which was the smallest prime dividing the order of the group. And then it said if we pick a subgroup H, which is of index P, so in some sense it's like as large as possible but still being a proper subgroup. Then we showed that that subgroup H was necessarily normal by basically defining a group action and looking at the counting argument and having to deduce a lot of things, but essentially it came down to showing, as you can see from the end of the argument, that GH, G inverse stays within H. And yeah, that's basically our definition of normal. So yeah, I think this is a nice problem. It really illustrates the group action stuff really well. And I said this at the beginning of last time, but there is some stuff at the end of Jacobson in the first chapter that talks about the CELO theorems. But my personal opinion is that probably too much to be done in a little video like this, and a lot of it is really just applying this group action stuff. So a lot of it is going to be a lot of the proofs are going to be very similar to the proof I just did today, where you're defining a group action, you have to figure out what's the group that's acting, what are the sets that it's acting on, how can we use the counting formula to deduce, different things about the orders of subgroups, normality, etc. Okay, so I think that concludes the group theory stuff that I wanted to talk about. Like I said, if anybody else has anything else they want to ask me about it in group theory, I can always revisit it. But I think Friday we're going to delve into some calculus topics, and eventually maybe we'll end up in statistics, financial mathematics, something in that area. So I'm going to start making some calculus videos. Hopefully they're more like appealing to a broader audience, a lot of college students, undergraduates just starting out. They might need some extra help. It's always good to see the information from another perspective or from another set of eyes and another mouth. Okay, so yeah, that's it for group theory, and I'm going to sign off now, and I'll upload the video to YouTube.